Welcome to WebGoat's A2 Crypto Basics, where today, our mission is to learn the basics of encoding and encryption, and then use these to discover a password that's supposed to be inaccessible. As always, before we get into the module, I'm going to not so briefly touch on some core technologies used. First, let's talk about the Unix command line. You can click the link on the top right to visit a great video about this by Network Chuck. In this video, he talks about the 60 most important Linux commands to know, and while this might seem like a lot of commands, we're only going to be using a select few of them. More specifically, the echo, su, ls, cd, cat, and rm commands, as well as two additional ones he didn't cover in his video, these being sed and cut. Sed can use the -e option to apply a regular expression to a string, and cut is a command that can take a delimiter and then cut a string into sections so you can pick one of the fields. The second thing I want to cover is going to go into more detail on the encoding segment from one of the earlier videos in this series. There are many different types of encoding, but in this video, we're just going to cover base64, XOR, and URL encoding. So let's start with base64. The character set of a base64 encoded string contains the 64 characters that are available in most character sets, which includes all uppercase and lowercase alphabet letters, numbers 0 through 9, the plus and / characters, and finally the equal sign, which is used for padding. If you don't care to understand the nitty-gritty details of how base64 actually encodes a string, I'll go ahead and put the timestamp to the next segment on the screen, so you can skip this segment if you want to, because it's not actually important to understand how base64 works to use it. So base64 converts every 3 bytes of data into 4 base64 characters. Each base64 character is made up of 6 bits. For example, the word hi with an exclamation mark can be represented as this 24-bit long binary segment, or 3 bytes. Base64 will divide the binary data up into 6-bit chunks and then map them to a base64 character according to the table. Therefore, the base64 encoding of hi is SGKH. Now I know that I mentioned that equal signs are used for padding, which can occur, for example, if you say hi without an exclamation mark, which when converted into a binary sequence is only represented by 16 bits, which is not divisible by the 6 that base64 requires. So base64 will add zeros to the end of the bit sequence. These zeros encode to an equal sign. Therefore, the base64 representation of hi without an exclamation mark is SGK equals. So now let's talk about XOR encoding. An XOR cipher uses a random generated key to perform an XOR logical operation on data. An XOR operation just means that it's going to return true as long as one value is false and one value is true, meaning if they're both true or they're both false, the XOR operation returns false. This can be reversed because if you run an XOR operation on something that's already had an XOR operation performed on it, it reverses it back to its original state. And the last type of encoding we're going to talk about is URL encoding. There is a set of characters that's illegal to include in a URL. So in order to include those characters in a URL, you can convert them to their UTF-8 values, which consist of a %sign and then a hex value. This can then be reversed by the browser or the server by converting the UTF-8 values back into ASCII values. Okay, now that we're done with encoding, please note that you can't use any of these for encryption as they're all predictable and easily reversible. The next technology we need to cover for this module is hashing. Some of the main hashing methods you'll see around are MD5, SHA-1, and SHA-256. And the way that a hash works is similar to encoding, however it's irreversible. So you might be wondering, how do we access the data after it's been hashed? Hashed data can only be accessed by hashing a new string and then comparing the new hash to the hash value that you already have stored. If the two hashes are equal, then the value that you just encrypted is the dehashed version of the hashed value. Hashes are most commonly used for things like passwords, as you don't really need access to the original password, and whenever a user authenticates, you can compare the hashed value of what they input to the stored hash of the password. So now, the last technology we need to get into before the module is signatures. There are 2 basic types of signatures, symmetric and asymmetric signatures. When a signature is symmetric, this means it uses the same key to encrypt and decrypt the data. This is best used for resources on a single machine that are not leaving that machine, such as encrypting a zip file. Now, when a resource uses asymmetric encryption, it means that it uses a mathematically related pair of keys for encryption and decryption, a public key and a private key. The private key contains a lot of values, most importantly a modulus and a public exponent, and the public key contains both of these values as well, using the modulus to create and or verify the signature, and then using the public exponent to decode the original data. Whew, okay, you made it. So let's get into the module. Okay, so now since we've already covered all of this information, we can go ahead and move straight into the first section. This section starts off by explaining how base64 works, and then explains to us how it's always used in an HTTP authorization header. It then provides us with our own header to try to decode. I'll leave a link in the description to all the websites I'm going to use today, and we're going to start off with this base64 decode website. Copy and paste the authorization header straight into this website, and you'll see that it decodes to your username and then 123456 for the password. Now we can move into the next section, which starts off by explaining different types of encoding. The one that we'll be using here is XOR encoding, and I found the most reliable decoder is the one provided by WebSphere. Again, there's a link to this in the description, so go ahead and paste in your XOR cipher on the left side and hit decode. Note here to delete any spaces that you may have accidentally copied, and we can see that this cipher decodes to the string database password. Copy and paste this back into WebGoat and move on to the next section. In this third section, we're provided 2 hashes, but it doesn't actually tell us what kind of hash is being used. This is where we can use a hash identifier tool like the one linked in the description. So we'll start with the first hash and paste it into the identifier to find out that it's MD5. Now usually the best way to start decoding an MD5 or SHA-256 string is to copy and paste the whole hash into Google, as many times you'll find that commonly hashed words are copy and pasted all over the internet. After searching up this first hash and putting MD5 after it, we can see that it decodes to password. So let's move on to our second hash and place it into the identifier, which after doing so, we find out uses SHA-256. I'm now going to paste the hash into Google, followed by SHA-256, to find out that the hash decodes to 123456. Type or copy and paste this into WebGoat, and we can move on to the next section. Once we move into the next section, we can see that it starts by explaining to us how a raw signature is calculated. A hash is created, and then it's encrypted using a private key, and then it's decrypted using the public key. The public key is served in a certificate between the server and the client, and this certificate ensures data integrity. So for the assignment, we can see that we're provided an RSA private key. We're supposed to decode the private key, and then provide the modulus, as well as create a new signature based on that modulus. Refer back to the section in the beginning of the video on this if you need a refresher. Okay, now let's get into the scripting. I'm going to create a new bash file called getModulus.sh, and the first thing I'm going to do is I'm going to create a variable called private key, and it's going to be set equal to a variable that we're going to set in the command line when we call the script. We're then going to take that string and remove all spaces. Now we're going to create a private.key file, and we're going to first echo into it the begin private key line that we need for a private key, followed by our private key variable. And note here that I'm going to add a new line after every 64 characters, as this is how a private key is formatted. The last thing we're going to do with this is we're going to echo the end private key into the private.key file. Now these next few lines aren't required, but they are nice to have as it helps to verify the status of the file before we move on. Now I'm going to create a new variable called mod, and it's going to run this openSSL command, which takes the -modulus option, forcing it to return only the modulus. Now this is going to return a string that looks something like this, so I'm going to cut it by the equal sign, and I'm going to grab the second field. Echo that out into the command line, and now we have our modulus in the terminal. The last thing we're going to do is we're going to call a getSignature.java file with a key and mod environment variable, and then we'll jump over and create a new Java file called getSignature.java. In this Java file, we're first going to create message and private key variables that are just going to grab our environment variables. I'm then going to convert the private key string into a private key object using this function getPrivateKey from PEM. Moving down to the function, we can see that it removes the begin and end private key lines, as well as removes any new line characters. Now we have just the key itself, and we're going to base64 decode it. All that's left is to convert it into a PKCS8 encoded key spec, and then generate that into a private key using Key Factory with the RSA algorithm. Moving back to our main function, we're now going to create a new variable called instance, and in that we're going to store the RSA algorithm. We're going to start a new signing method on that variable, and then we're going to use it to convert the modulus into UTF-8 values. Now we can create our signature. All there is to this is to base64 encode our instance variable, and then convert that whole string into UTF-8 values. Now again, this last section is unnecessary, but it helps to keep your terminal clean and organized. So now we can run this script by copying our RSA key from WebGoat, and then going to terminal and calling sh getModulus.sh and then the key. You'll see here that the output will return a modulus as well as a new signature. Copy and paste these into WebGoat, and we can move on to the last section. Now, loading into the last section, we can see that there's an RSA private key hidden somewhere within the Docker container for this assignment. So we can start by opening our terminal and using Docker to run the assignment. This gives us the ID of the Docker container. So now let's start by running bash within the container, which can be run by using docker exec-it, then the Docker ID, and then /bin/bash. Now that we're in the Docker shell, let's first start by trying to change directories to the root directory. Upon doing so, we can see that we have permission denied, so let's find a way around this. If you look through all the folders, you'll find that in the etc directory, there's a file called password. Now, in the Docker shell, we don't have access to nano the file, so instead, we're going to exit the Docker shell, and we're going to use Docker to copy the file onto our desktop. Once we take it out of the shell, we can edit it however we like. So upon opening the file, we can see that root user has an ID of 00. This differs from WebGoat's ID of 1000, so we can simply change WebGoat's ID to 00 to allow us to have root access to the shell. Now we can use Docker to copy this file back into its original directory, and then we can re-enter the bash shell by rerunning the command we ran earlier. Now if you try to access the root directory, you can see that we indeed have access. You can also see there's a file in here called default secret. If you cat the file, you can see that it contains the password used to encrypt the message from WebGoat. So now to decrypt that message, we can use the echo command from WebGoat. This command already contains the encrypted message, so we can simply copy and paste the whole command into our terminal. After the -k file option, put in the name of our secret file. Once you hit enter, you can see that it provides us the unencrypted message. Copy and paste this into WebGoat, and then for the name of the file, put in the name of the file we used to decrypt the password, default secret. And this marks the completion of WebGoat's A2 crypto basics. I know this was a long video, and I appreciate you sticking with it through the end. This information is super important to know, and understanding it thoroughly will help with a lot of modules in the future. So thanks for watching.